So the third part of this lesson is curve fitting. This is a technique usually used to build something called standard curves. This is when we need to determine the concentration that we don't know, but we will not measure directly the concentration. We will measure some signal and the concentration of the substance must be proportional to the signal of that measurement, and we will build some linear regression to construct the curve. For example, if we have a series of solutions with increasing concentrations of something, and we use chromatography to separate and determine it, and you will have some peak area. It is a signal from the chromatography device, and this signal will be proportional to the concentration, and we can build a line like this, right? And the equation of this line, which is called linear regression, will tell us the relationship between the peak area and the concentration, and this relationship is linear, right? And the relationship is often written by an equation y equals ax plus b, right? And we have the slope. The slope of this line is a, and b is the intercept with the y axis. So this is another example. For example, if you want to determine concentration of BSA, bovine serum albumin, right? You will prepare a series of solutions with the standard BSA, and then you measure the absorbance of the optical absorbance of these solutions, and then we have a series of points like this, and then we use very simply Excel, Microsoft Excel, to build this equation y equals ax plus b, right? And 0.0014 is the slope. It is called the slope, and 0.1186 it is the intercept, right? And r square is called coefficient of determination. And all this equation and this r square, it is calculated by the software. We don't need to do anything. We don't need to do any calculations. Another thing to remember that this regression line is not 100% correct. It will have its own error. For example, in this graph, you have 5 data point and a regression line, and this is the equation of this line. And it has looking at this correlation coefficient, we see that this line is not very fit to the data, and so it has relatively high errors. So the slope and the intercept will have errors, and the whole equation will have its own error, and the true line will be inside an area. This area is from the upper limit to the lower limit, right? So every time when you have one value of x, for example, in this case, you have a concentration of 60 ppm, and using this line, this equation, you will determine the peak area y, right? And you will have one value, but remember that this value will have its own error. So the true value of peak area will be inside some range, and this range will be between this and this value, right? The lower limit of the peak area is determined by the lower limit of the regression line and this value of concentration, and the upper value of peak area is determined by the upper limit of the regression line and the concentration value, right? So how can we lower the amount of error? The first way is to include more replicates of the data. This means that for each of these data, you should conduct more experiments. So, for example, at this value of concentration, you should prepare 3 or 4 solutions, and then you measure the value of peak area. So this is the first way. The second way is you expand the concentrations more than 8 points. So in this example, we have only 5 points. So we should add at least 4 points more. Maybe inside this area, right? You can add the 4 or more points inside this area from 5 to 100 ppm. And in our online class, we have 2 video which I instructed to build the calibration curve using linear regression in Excel. Right? You just click on this link, and then the second video. Please pay attention that these 2 are the same. Right? The second video is how to construct the 95% confidence interval for the linear regression equation. Right? So please watch these 2 videos and do as instructed, and then you will know how to use Excel, Microsoft Excel, to build the calibration curves. So every time you use Excel to calculate this equation of regression, Excel will automatically calculate R square for us. R square is called coefficient of determination, and R is called correlation coefficient. This correlation coefficient R tells us how well a model, usually we have a linear model, fits the data, right? And we have, this is the formula for R, and the closer R to 1 or minus 1, the higher the correlation between X and Y. In these 2 plots, you will see 2 examples of data and correlation equation. On the first plot, you can see that these data points lies very close to the line. So we say that the correlation is very well between Y and X, and you will see that the value of R in this case is very close to 1. On the second case, you can see that these points lies relatively far from the line. It means that this equation, this line, does not fit well to the data, and you will see that the value of R is relatively smaller than 1. But usually we will use the coefficient of determination, which is R squared. This is the portion of data variation explained by the model, by the equation. So for example, if you have R squared equals 0.99, this means that 99% of the data variation can be explained by the equation. So the higher the value of R squared, the better the model. And so often this coefficient of the determination is often used because it gives a better perception of the straight line. So it tells us directly the percentage of data variation explained by the model. And although it does not indicate the direction of the correlation, because for R, you can have a positive or negative, because we can have positive or negative correlation. For example, in this plot, you can see that when we increase the value of X, Y will decrease. So we say that between X and Y, there is a negative correlation. And in this case, you can see that the line is flat, so it is horizontal. This means that there is almost no correlation between X and Y. So remember that when the slope is close to zero, the correlation is very weak.